Okay, let's continue with some kinematics here. Oh man, come on. Color do we want? Let's go with some this kind of blue. Yeah, I guess it is. Kinematics continued. All right, so all right, let's go right from scratch here. Okay, so we've been talking about motion with respect to a number line. Okay, so we'll just kind of keep that going on. And we know that as objects move around on a number line, okay, they have initial positions and final positions. And we worked out the other day that you can find the velocity of an object, which is its rate of travel, by looking at its change in, or its displacement, I guess, its change in position over how much time that took, right? And this is going to be measured usually in meters, and this is going to be measured usually in seconds. So the units for that will be meters per second. Sometimes kilometers per hour, depending. Okay, so there's a little bit of a correlation to graphing here, okay? So let's just say we have an object, I don't know, moving along, say towards the right, like this. So I'm just going to remind you of some stuff that you did last year real quickly because we're going to use it to build on what we're doing this year. Okay, so if this is a displacement time graph, or I should say a position time graph, all right, this object starts at 0 and it moves to the right. Okay, like this, and like this, right? And we take this here. What we're going to see is the object, you know, extending into the rightward direction as time goes by. If the object moves really fast, we're going to see this, right? It's going to cover more ground in less time. If the object moves really slow, we're going to see this. It takes a long time to move much. Do we agree with that? Okay. And we're going to realize pretty quickly, I think, if we look carefully, that that's a run and that's a rise, and that we said we defined change in position as displacement, right? So that's pi. Okay, it's pi, so some point here, and then some point later in time, we're over here. That's my final position. So these are the 2 points I'm looking at, right? pi and pf, all right? And then we know that that takes some time, but if my time is here, tf or ti. Well, what I'm finding here is slope is equal to rise, or delta d, over run, delta t. Aha! The slope of a displacement time graph gives me the velocity, right? The rise over the run is velocity. It's an important thing to remember. You with me? Okay, great. Now, the second thing is, well, what if instead of a displacement time graph, we graph the velocity of the object as time goes by? And we'll use this same object. We'll say this one here. Okay, so if I make another kind of Cartesian graph here, like that, and like that. So now what we're going to do is monitor what's happening with the velocity. Well, we'll see that, does the velocity ever change? Well, no. The slope of this line is always the same, so the number we get here will always be the same. So if we plot that as a velocity time graph, what do you expect that we'll see? Will it be changing, or will it be a flat line? Yeah, it'll be a flat line, right? So what this is saying is the velocity, if this is a velocity and this is a time, as we monitor this velocity, it just never changes. Well, what if we looked at this? How would that change this? What would that do if we looked at this slope instead? Yeah, it would be a flat line but higher up. And if we looked at this one, it'd be a flat line, but it'd be lower down. Okay? So we want to know, what is the relationship, or how does this work with this? Okay? So if I take this formula and I rearrange it, I can get this out of it. I can say that my displacement is going to be equal to whatever velocity I'm traveling at multiplied by the time that I travel at that velocity. In other words, if I travel at 100 kilometers per hour for 2 hours, I've gone 200 kilometers. Correct? Does that make sense? So if you look here, I'm saying I multiply velocity times time. Have a look at this graph. Here's the velocity, here's the time. If I multiply velocity times time, what I'm really finding is the area under this curve. Not really a curve, it's a line, but the area under this line. So the area under a velocity time graph, let's do it like this, velocity time graph is displacement. Okay? So that's a pretty important thing to have at the ready at all times and know. Okay? So the first thing is slope of dt is v. Slope of a displacement time graph is velocity, or a position time graph, I should say. Slope of a position time graph is velocity. And area under a vt graph is displacement. Right? So this is the displacement at a given time, right? If I only go this far, well, that's my displacement. I go to the end of the time, that's the total displacement that I have from my starting point. All right, so going this way is slope, going this way is area under the graph. So these are related to one another, and they obviously are. They're talking about the same motion. Okay. Now what happens if instead of having a constant velocity, we have an accelerating object? This is where it gets a little more interesting. So here's your number line. Uh-oh. Let's try that again. Here's your number line. Let's populate it. Okay, so we'll just have an object accelerating to the right to start here. So if this represents, constant time intervals, we're going to see this object speed up as it goes to the right. So it's getting faster and faster and faster as it goes. So we want to see what that looks like as a displacement time graph. Can anyone tell me what it will look like? It will be a curve, exactly. It'll be a curve because my velocity is constantly increasing, right? Velocity increases. Velocity is increasing, that must mean the slope of this line is increasing, right? Because we said before that, if this is a position time graph, the slope on here is velocity. If that's traveling at a constant velocity, that's fine. We just have a constant slope. But if it's speeding up, the slope is always changing. A constantly changing slope looks like a curve, right? And we know this because if we look at the slope at any given, split second in time, the slope here is low, right? There it is. That's what the slope would be like right at this point. Then later, the slope is a little bit higher, right? See, there's the slope for that little bit of time. And so on. The slope gets a little higher over here. So what we're saying here is that the instantaneous velocity, the velocity at this exact moment in time, whatever that happens to be, the instantaneous velocity is the tangent line to our curve. Okay? So if we can know what the tangent is, we can figure out at exactly this point in time how fast I was going. Back here I was going slow, here I'm going faster, here I'm going fastest. The magnitude of my velocity is increasing as time goes by. If I want to know exactly how fast I was going at like 8 seconds, I've got to find the tangent. Okay, so there's a constant increase here. So what that means is, if I look at all these individual tangents, right, every second I say look at the tangent, what I will find is that the velocity gradually increases, right? At time 0, velocity was 0. At time 1, that velocity might have been 1. At time 2, velocity was 2. Okay? Etc. So what I'm saying here is, every second, I'm going 1 meter per second faster than I was before. Does that make sense? So if this is the numbers I get from here, I could say each second I get 1 meter per second, and it could be 2 or 5 or whatever, 1 meter per second faster. Or I go faster by 1 meter per second, which gives us this new unit of 1 meter per second squared. And this is the unit of velocity, the meter per second squared. Okay, this is the general, we don't deal with kilometers or minutes or anything like that. Acceleration is pretty much always dealt with in terms of meters per second squared. So we're saying this, at the beginning, was 0 meters per second. Here at 1 second, 1 meter per second. Okay, here at 5 seconds, 5 meters per second. At 10 seconds, 10 meters per second, right? The slope is increasing, our velocity is increasing, we are accelerating. Okay? Now let's say we took this data and we wanted to make a velocity time graph out of it. Well, our velocity time graph is going to look a little bit different than it did before. It is going to be like this now. Here's our velocity time graph. Velocity, time. And what did we say? We said, well, every second it increases by 1. Okay. This unit is the meter per second. This unit is the second. Here's our time. By. This is a velocity versus time graph. We want to be real technical about how we label everything. And we're going to find this. Okay. Make this an arrow. We're going to have that. Okay? All right. So the first thing, before we do anything else, is let's take a look at the slope here, right? I just want to tackle that first. Okay, so the rise now is delta V, right? It's VF over VI, or sorry, VF minus VI, right? And the time is delta T, so TI and TF. And our slope then is going to be delta V over delta T. Aha! What did we learn last year that a change in velocity, or the rate of change in velocity, is called? That's acceleration, absolutely. A equals delta V over delta T. So, what we're saying then is the slope of a VT graph is what? Excellent. The slope of a VT graph is acceleration. Well, let's just deal with that then. What the heck? While we're at it, what does the equivalent acceleration graph look like to this object? Is it accelerating? Yes. Is acceleration constant? It is constant if this line is straight, right? The slope never changes. So the acceleration never changes. So there's a mirroring effect here as I like to call it like inception, as we like go one level deeper, right? So now we're saying we have an acceleration here. If I go way back up to where we started, was there an acceleration here? Well, no, there's no slope on our velocity time graph back here, right? If we're traveling at a constant velocity, there's no acceleration. That makes sense. There's zero slope here, so my acceleration time graph is just empty. Nothing's happening on it, right? But now something is happening on it. We've got a straight constant acceleration, right? Well, if we rearrange this formula, it becomes this. Delta V is equal to A times delta T. Ha! Here's my time. Here's my acceleration. Acceleration times time is the area. Area under an acceleration time graph is velocity change. Which makes sense. If my acceleration is 1 meter per second squared, after 5 seconds, how fast am I going? Well, 5 meters per second, right? 1 meter per second squared times 5 seconds, 5 meters per second, right? So the area under here tells me what my velocity is, what my velocity change is. My velocity is changed by 5 meters per second. It's increased by 5 meters per second in this case. So area under a t is a change in velocity, right? Just like our formula said. Now, what did we also say about the velocity time graph? We said that the area under a velocity time graph gives us what? Earlier on, what did we say? Good. Recall. Area under a VT graph gives displacement. Dot, 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 dot. So, let's just bring that, let's use straight lines. Let's just bring that graph back up. Okay, our velocity time graph that we just made, let's bring her back up. Put her back in the mix. It looked like that, didn't it? Okay. And we said before that the area, velocity times time, is going to be my displacement. We agree with that, right? But this is only if we have a constant velocity, right? This is no longer true in this form for an object with a changing velocity, is it? So we have a VI here, and we have a VF here, and we have a TI here, and TF here. So my question to you is, it's true that the area under here is still going to be displacement, but it's not true that I can directly do it like this. So how do we find the area of an object that's shaped like that? So to find an area of an object that's shaped like this, we have to just think about this a little bit here. All right, so I'm just going to highlight a couple things. And our original triangle formula that we learned just says base times height divided by 2. The reason being is because that makes a box, right? And if you cut this box in half, you have the area of half the box, right? Base times height divided by 2 is like cutting the box in half. Are you with me? But we could also cut the box in half another way and end up with an area equivalent to this. We could take the box and we could cut the box in half this way. Couldn't we? Just to make sure that we're completely understanding that, let's just review it, because I know sometimes these things like to gloss over you. Here's a square, right? The area of this square is b times h. Okay? If I cut this square in half, use a color you can see, we cut it in half, right? And we only want half of the area of this square. You could say that this area right up here, or actually right down, or wherever, doesn't matter. This area down here, let's make little bubbles in it. This area, right? Well, this area should be b times h over 2. Do you agree? Right? And we could also say this. Another way to cut this thing exactly in half is to do a diagonal. All right? And let's put like, I don't know, little stripes on this. That area is also b times h over 2. Okay, are you with me? Now, something else that we could do is we could say, well, what if we just call this like, I don't know, let's call this like H1 and this H2. Okay, and I'll see, we'll go back to our graph in a second. Could I call this height H1 plus H2 divided by 2? It's halfway between the two, is it not? So halfway between the two is like adding them up and dividing by 2. In other words, it's like the average. Okay? Now, why am I doing that? Well, because I want to show you that the area under this sloped line and the area cut by this here are the same. Do we agree with that? They have to be the same. They're both half this size, right? So what we're going to do is come back to our drawing, right, which is our velocity time graph. We're going to say this. If this represents VI and this represents VF, we could call this VF plus VI over 2. If you don't believe me, let's actually put values in here. What if this was 10 meters per second and this was 0 meters per second? Well, halfway between them, 10 plus 0 divided by 2 should be 5 meters per second. Okay, so if I take VF plus VI divided by 2, I get that. If I want the area under here, I got to multiply it by time. So what we're saying here is, for an accelerating object, the displacement is found like this. D, for an accelerating object, is equal to VF plus VI over 2, that gives us this line here, times time. There you go. This will allow you now to find out how much distance an object covers while it's accelerating. Okay? And there's one other formula that's going to come in handy. Okay? So there's a new formula for you, and we're just going to take an old formula and we're going to dissect it a little more. Okay. So here's our other formula that we've had from before, and we could say this, right? VF minus VI over delta T. And we could do a multiplication. We could say this. VF minus VI, multiply both sides by delta T. Like so. Gives us acceleration times time, or delta time. Okay? And we'll do one more little motion. We'll say the final velocity of any object is its initial velocity multiplied, or added, sorry, to its acceleration times its time. Okay. Let's write that a little more clearly. Right there. Okay. So what have we learned today? Well, we've basically derived two handy new formulas. We've got that the displacement of an accelerating object is VF plus VI, its initial velocity, plus its final velocity, over 2, because we want the average, times time, and that the final velocity of an accelerating object is however fast it was going at first, plus how much that velocity has changed, right? Change in velocity is AT. Please add these to your collection. Okay, they're actually on your formula sheets. And then put them beside this. D equals VT. Well, you didn't actually write it that way. You did this. Velocity equals delta D over delta T. And our very original one, or sorry, not our very original one, our other original one. There. So you now have 4 formulas that apply to different scenarios. Okay? This is for constant velocity. You got to be very careful. This is for accelerated velocity. Okay, you can't use them in the same situations. They apply to different scenarios. And that's it.